Okay, we're gonna do example 3.9 together. Um, I'm gonna add to their givens here. So the situation is that we're trying to find the speed at which this person is going to be shot from a cannon. Um, and so what we're looking for here is V0 or V naught, which you can see here, V0 equals question mark. And I'm going to add to their givens a little bit. I'd rather, split them into the X and Y direction. So I'm going to rewrite the givens for this human cannonball problem. So when I write them separately, I'm going to have X direction. Okay, so we are saying that this spot here is X0, and that's going to be 0. And um, we know that the net is 40 meters from there horizontally, so that's at time t, that's 40 meters. Okay. We know the velocity in the x direction. Okay. That's going to equal whatever the velocity was to begin with times cosine of 45 because they're being launched at an angle of 45. So here, this initial velocity vector has an x component that would be adjacent to the 45. Now, of course, cosine, sine, and 45 happen to be the same number, okay, but sometimes it's not going to be 45. All right, and then acceleration in the x direction is going to be 0 meters per second squared. I just like to keep them separate. Okay, then y direction. Okay, we're going to say that y0 is also 0. So even though the person is clearly above the ground when they begin, because they're going to land at the same elevation, then we're going to say that both um, y at time 0, height at time 0, we're just going to say that is 0. And then we're also going to say, that final position, because we're landing on the mat here, which is at the same elevation, that's 0 as well. So 0 displacement in the y direction. The velocity in the y direction would be initial times sine of 45. Okay, so again here I would find the V0 y would be opposite of the 45-degree angle. Okay, and then acceleration in the y direction is negative g, or negative 9.8 meters per second squared. Okay, now what they have in common though, right, is the angle, the initial velocity, and the time. So if we want to know the speed that she needs to come out of the cannon with, then the first thing we could do is actually find time, because we can't solve for v sub 0 without knowing that first. We know that gravity is what's going to make her fall down at the time she does. So let's pick the y direction and solve for time first. So let me scroll down. And okay, so let's use y direction. Use okay. Um, there there are a couple of right ways to do this. I'm going to use this equation here. Um, it's on your formula sheet, except for it has x's instead, I believe. But because we're dealing with the y direction, we just have y's in here. So I'm writing the whole thing out. this is y direction. Okay, so we have a displacement of 0. So this is 0 meters at the end. It began at 0 meters. Then we know that a fraction of its velocity was in the y direction times time plus 1/2. Okay, I'm going to leave negative g in here, and then later I'll put the negative 9.8 in. Time squared. Okay, well, since this equals 0, there are two solutions here. Let's factor out time. So if I take 1, this goes away. They're both, you see time in here. So if I factor out delta t, one of them, I'm going to end up with delta t times v naught times sine 45 plus 1/2 times negative g, and then I've got 1 delta t left. Okay. So now there are two solutions here. At time 0, it's definitely 0. Okay, that's not really the time I was looking for, though. I knew that he was, or she, was at 0 seconds. So that's one solution. That's not the one we want, though. So we can also say that another solution would be when this whole part equals 0. So let's set that equal to 0. V naught sine 45 plus 1/2. Okay, and then what I want to do is get t by itself. So if you do that, okay, let's see, I would say add half gt to both sides maybe. So g delta t, because this is negative, see here? Okay, so if I do add that to both sides, then this becomes positive. Okay, this is just algebra. Okay, and then get t by itself. You would have over g. Okay, so I'm going to leave that like that for now. But now that I have time in terms of initial velocity and g, which is a constant, that's great because then I can solve for v naught, because look, I know the displacement in the x direction, so that gives me more information I can use and solve for v naught. So now we're switching back to the x direction and plugging in time. So let me scroll this a little bit. So we're going to substitute delta t into x direction equations. Okay. So for x displacement, now I know there's a simplified formula in your notes or in the book. I'm just going to write it out just like it is on the formula sheet, though. Okay. With the whole thing. Oh, silly me. Plus 1/2. But remember, it's not accelerating in the x direction, right? So anyway, I've got 40 meters as my position at time t. It started at 0. It's going, v0x is really just part of v0. Oops, cosine technically, but you'd get the same thing. Cosine 45 degrees, that's what v0x is. Okay. All right, then delta t, I'm going to plug in this whole thing right here. So now I'm going to do 2 v naught sine 45 degrees over acceleration due to gravity. Okay, that is that whole thing. Okay, but then ax is 0 because it's moving at a constant velocity in the horizontal direction. So that all comes out to be 0, which is nice. Okay, so then I'm just doing algebra, and if I multiply all this out, there's a 2 here, and sine 45 times cosine 45 works out to be half. So then all that goes away. So then I'm left with, I think, 40 equals v naught squared over 9.8 meters per second squared. And then I'm solving for v sub 0, and I end up getting about 20 meters per second, which is reasonable. I mean, it's a powerful cannon, I guess. Okay, we're done.